Hey students, Mr. Halpern here. This is a video on temperature and volume relationships and how we can quantitatively study that using Charles's law. So you should just put on the top there next to temperature-volume relationship Charles's law, because we'll often refer to that relationship with that law. So if you can recall that the fourth part of the kinetic molecular theory talks about how temperature, particularly how heat energy, can excite the movement and change the movement of the gas particles to the point where they start to have more kinetic energy and therefore more movement and more collisions with more force. And as a result, this will, if you think of a balloon or something like that, as the kinetic energy of these particles increases, you're going to have, particularly for an expanding surface, you would have a volume that the gas would want to take up that would be larger. So, in other words, the volume of the gas is directly proportional to the temperature of that gas. One more time, the volume of a gas is directly proportional to the temperature of that gas. Over to the right, there's a graph that depicts this relationship. As you can see, as temperature increases, going from negative 250 degrees Celsius to 50 degrees Celsius, the volume that the gas takes up increases. And it varies slightly depending on which gas you're talking about, but the general trend is all the same. So just like Boyle's law, Boyle's law was a quantitative way of measuring the relationship between pressure and volume. Charles's law was mostly created by Jacques Charles, who is a French chemist, and he studied the changes of gas volume as the temperature was changed of that gas. And what he did was he tried to keep the pressure constant. Charles decided to use Kelvin, which is a new type of temperature scale that we haven't talked about, and together with Kelvin, who was a lord, he was an English scientist, they created this quantitative equation. So it's important to note a couple of things here. First off, with Boyle's law, you had pressure multiplying volume. In this case, you have volume, being divided by temperature. And the second thing to note as you write this down is that the temperature is in Kelvin. And the way that we figure out Kelvin is by taking the degrees of Celsius and adding 273. So for example, I'll just do a quick little example. If I give you degrees Celsius is 35, well, then I just plug this in and I add 273 to 35. So therefore 35 degrees Celsius is equal to 308 Kelvin. And I represent Kelvin with an uppercase K. So even if I give you a problem, or if you find a problem on a worksheet or a quiz or a test, if we're talking about temperature, we want to convert Celsius into Kelvin. Sometimes we'll give you Kelvin, so you won't have to do that work, but sometimes not. So your example here, let's say that you buy a 5-liter helium balloon in a mall. Maybe it's a birthday or something that you want to purchase a balloon for a mom or a dad. And you go outside and you place the balloon in a car during the winter. And you go outside and the temperature inside of the mall was 24 degrees Celsius, but the temperature in the closed car on the outside was a lot colder, 70 degrees Celsius. So what will you see over time? Well, as you leave the balloon in the car over time, what should happen is, because the temperature is decreased from the mall to the closed car, the volume is going to decrease. Again, why was that? Because we said above, the relationship between temperature and volume is that the volume is directly proportional to temperature. So as the temperature goes up, volume goes up. As the temperature goes down, volume will go down. Now we can actually solve this. What will be the new volume of the balloon? Well, we know the original volume is 5 liters. We also know that the initial temperature is 24 degrees Celsius. We know the final temperature is 17 degrees Celsius. And what we don't know is the final volume. So we plug these numbers that we have into the equation. V1 over T1 equals V2 over T2. Remember from the previous formula from Boyle's law that the 1 or the 1s represent the initial measurements, and the 2s represent the final or resulting measurements. So the initial volume, V1, is 5.0 liters. The initial temperature was, did you see what I did there? I put it in Kelvin. Remember, how did I get this number? I had to get this number in Kelvin. Well, what I did was I took 24 and I added 273. Okay, and then I also did the same thing for T2. I took 17 degrees Celsius and I added 273. Okay, and when I do this and I solve for x, I take 5, multiply it by 290 Kelvin, and divide it by 297 Kelvin. And I get that the new volume, it went down from 5 to 4.88 liters. So it decreased by 0.12 liters. And that makes sense because the temperature went down, so the volume should go down. As a connection to a real-world application, on the right-hand side, I have a picture of hot air balloons. So the question is, why does a hot air balloon rise? Well, if you add hot air to the balloon, the volume of the air will rise. Also, the pressure, well, let's just stick with that, I guess. But the kinetic energy is going to increase because of the heat, so the volume will increase. Okay, and so as a result of the volume increasing, the density becomes lower than the gas on the outside of the balloon. And because the density of the air inside is lower than outside, the balloon is actually going to rise. Okay, so that is Charles's law and the relationship between temperature and volume. Take care.